which actually will help us understanding few things that we left over. Well, actually I didn't write on my notes the first example, but it should be example 1. And this is actually one of the most common. So we need two surfaces, and the question is whether they are isometric or at least locally isometric or not. Well, actually, let's take as a first example, as a first surface, the plane itself. Okay? As usual, no problem. Let's say the plane x is equal to 0. So of course we have a very standard chart for that, because the identity map from the whole of R2 to the plane. So in fact, x1 in our language, from R2 to S1 would be just u v going to u v 0. So of course what the proposition is hinting is that we should know the coefficients of the first fundamental form. In this case, of course, everything is obvious. What are the coefficients of the first fundamental form? E1, F1, G1. So XU is 1, 0, 0. So, okay, so that's of course very trivial. But now, as a second surface, let's take, for example, the right cylinder. Okay. So S2, remember, I think we discussed, when we discussed the Gauss map and the differential of the Gauss map, the right cylinder. So this is the set of x, y, z in R3. By that I really mean, for example, the right cylinder center on the z-axis, I mean, with radius 1, for example. I mean, that's not, so x squared plus y squared equal to 1. Okay. Now, how do I parameterize these surfaces? Well, there's a very simple way. If you think geometrically, actually the simplest way to parameterize such a surface, so this would be S2. So how do I get to S2 with, now I want to call it X2? Well, I just imagine that I have this line rotating around and covering the surface. So how do I phrase it? So this would be X2. Well, let me skip for the moment where I want to take it, but going to S2, and actually let me also skip where exactly. So I would take U and V. I mean, in principle, I could give a different names, but I mean, just U tilde, V tilde if you want. But well, in fact, let's do everything a bit more carefully, okay? So in principle, this is another plane, it's another piece of the plane. And where do I go? Well, let's say that the coordinate on these lines will be the U lines, okay? So I need to parameterize the circle. I parameterize the circle in the z equal to 0 plane, and then for each point I add the vertical line. So that means I'm taking what? Cos v, I decided that cos v, then I leave a little bit of space, sine v, no? So v would be the parameter rotating, and then the u parameter becomes u tilde, and then u tilde. Oh, no, I don't put anything here. Okay. Yeah, that's even more simple. Okay. Yeah, I would put the radius here if there is a radius, but this is 1. So you see, of course, the image lies here because x squared plus y squared is equal to 1. And then, what are the coefficients? So, and where actually do I want to see it defined? Because, of course, in principle, this would be defined over R2 again. But it has to be a chart, so it has to be injective. So, no conditions on U, because I want the whole line, but I need to take an open set of amplitude 2 pi if I want to take the biggest possible interval where it's injective. no? So I can take it, for example, times 0 to pi, but actually here I could decide to take minus pi pi, or whatever you want. I mean, anything of amplitude 2 pi, okay, where, okay. So let's take this one for a moment. The map itself will always look the same. I will just change this if I want to cover another piece of the cylinder. Very good. So which are the coefficients? E2, F2, G2? Well, x u tilde, no? I need to take x u tilde, and this is 0, 0, 1. So this is 1. F tilde, or E2, sorry, F2 is equal to, well, the scalar product of two vectors which have clearly nothing in common, because this will have, if I differentiate with V, this is 0. If I differentiate with U, these are 0. So this is 0. And what about G2? Well, this is minus sine cos 0. So if I take the square, I get again 1. Okay, so what does it happen? What did it happen? Now I look at the proposition and I say, oh, there are two charts. Now, are they defined over the same open set? Well, no. Strictly speaking, no. But that's just because I've taken the whole plane. So replace this with this. And then I'm exactly in the position of the proposition, because I'm saying I have two charts defined over the same domain, for which the coefficient of two surfaces, for which the coefficients of the first fundamental form are exactly the same. So the moral is, the pieces of these two surfaces covered by these two charts are isometric. Which are they? Well, on one hand, this was the plane, but I've taken not the whole plane now. I've taken just a slice. Any U is good, but V must lie in a strip of amplitude. Look, this is also a good, I mean, you will be teachers soon. Never teach after a trip to the US, okay? Jumping off the plane. Now I've put the origin here, and this is not 0 to pi, but, okay? So it's not this strip, it's another strip. Translate it up. Okay, I don't want to do it again. Then, so this part of the plane here is isometric to which part of the cylinder? Well, everything except what I would get with angle 0 or 2 pi. I mean, so here in my notation is what? It's x equal to 1. So except exactly this line here removed. No? Everything except one line. Okay? Of course, there is nothing important about which line. If you wanted to cover the cylinder minus another line, you would just change this domain here. Okay? And these are isometric. So this explains one of the. Remember when we did examples of computations of the Gauss curvature? We computed the Gauss curvature of the cylinder, and we found 0. And we said, well, this seems a problem. I mean, or at least it's interesting. We need to understand why. Okay? Because if the question is, Gauss curvature equal to 0 means flat, well, the cylinder is not flat in the common sense. Okay? But now you know what's going on. They are isometric, so they are indistinguishable in terms of somebody living on them. Okay? So maybe you will never be able to recognize whether you live on a cylinder or a plane, where if that's the whole universe you can see. Okay? Of course, there is one way you can recognize something, because actually this also shows that it's very different from being locally isometric and globally isometric. Because are the plane or the strip or whatever, any piece of the plane and the cylinder globally isometric? No. Why?
Because they are not homeomorphic.
Because they are not even homeomorphic. Okay, one is simply connected and the other has a non-trivial fundamental group. Okay, so you cannot improve it. I mean, you cannot say the cylinder and the plane are isometric, but an open dense set of the cylinder, yes. Okay, so this explains a little bit this little mystery about this. For example, a surface like the cylinder, it's actually a family of surfaces which has this property. So zero Gauss curvature. You shouldn't think that zero Gauss curvature implies plane. Okay, it's more subtle than that. But maybe locally isometric too. Okay. And in fact, let's see a variation of this, which maybe I can give it also partly as an exercise. It's a bit less intuitive. Let's take this one as a surface. But actually the other surface will always be a piece of a plane. Okay, we will discuss which piece. But as a surface, we take, how was it called? S2. We take now the XYZ in R3, such that x squared plus y squared is equal to z squared. Now, if I just stop there, there is a problem. Do you know, can you see which surface is this? Yeah, so it's not, I mean, there are two proposals. It's not this one, and it's this one. Okay? So it is true. The intuition was correct in the sense you slice it with horizontal planes, and these radii are growing either when you go up or down, because now there's a z squared here, so you can also go down. So this you can check is not a regular surface because it has a vertex, and this vertex is a problem. You cannot fix it. It's not obvious. I mean, it's not just because the picture is not nice. Okay, remember the cusp, no? I mean, whatever. So, but in any case, in this case, you cannot fix it. Here, actually, even topology helps you, no? Because of course, around this point, so there is even a topological problem. If this point had a chart, I mean, this type of object should be homeomorphic to a domain of R2. But then you remove one point and you have two connected components, on the other side there is nothing. So certainly you have to decide whether you want to take the upper or the lower part of the cone. So in this way, certainly you remove the topological problem, but then the corner is still a problem, and this is a bit more subtle to check. So let's say we take as a part of the surface the cone minus the vertex, a half of the cone minus the vertex, okay? So now this is a regular surface, okay?
But that's like a cylinder, right?
Is it?
Yeah, because we have the cylinder, we just make it the whole like shrinking, and it becomes exactly like that.
But when you say it's like a cylinder, what do you mean? It's homeomorphic to a cylinder, it's diffeomorphic to a cylinder, it's isometric to a cylinder?
It is diffeomorphic, yes. Because we can just like the R, it is homeomorphic to the unit interval, and we can make it bounded.
So, this is certainly true. You clearly have a map from the cylinder to the cone or vice versa, which is just remove half of the cylinder again, decide that the horizontal is the one going to the vertex, and then you just collapse this circle. No? That's true. But the question is, now we are in the world of isometries. Is this operation preserving length of curves? well, this one, no, for sure, because actually you said already, the magic word you used is shrinking. Well, but if you shrink, you change something, you change lengths, okay? Anyway, let's see what's going on here. So, in fact, I propose the following parameterization of this piece of the cone. I will tell you later, again, where I take the parameters. So first I write down the map. So I take x, u, v. Again, now I'm thinking of what? Of a half of a line, not the whole line, but half of a line rotating. But this time is not a vertical line. It's the bisectrix of one of the quadrants, okay? So, in fact, yeah, let's write it like this. It's u okay, where I will take u, well, u, you see, is the parameter, is essentially the z parameter. Now, these square roots are just there to normalize a little bit few things. So u is essentially the height. So it has to be positive, no? So u is in 0 plus infinity. And v essentially, it's essentially the rotation, okay, the rotation angle. So, but now it's normalized in this way. I need an interval such that if I multiply by square root of 2, I get 2 pi. So let me take it here. Okay, so that when I multiply by square root of 2, I get actually the whole thing, the whole rotation. Okay. Okay, let's do, this time it's a slightly less obvious. I mean, let's do the computation. What are the coefficients of the first fundamental form of the cone? What we call, but for that, of course, let me first write x to u, x to v, because this time I can make mistakes. So if I take the derivative with respect to u, what do I get? I get 1 square root of 2 cos v square root of 2, 1 square root of 2 sine v square root of 2, and then 1 over square root of 2, and then x to v is minus u, and then the square roots cancel, so minus u sine v square root of 2, u cos v square root of 2, 0. So let's write it here. E2, the first coefficient is what? It's 1 over 2, no? 1 over 2 plus 1 over 2. Okay, that's why, that explains why I've put this. So how much is F2? Well, if I take the scalar product, of course, here I should get 0, and I do, okay, because everything cancels, and G2 becomes u squared, okay? Okay. So, strictly speaking, you might say, well, now this is different. This is not the plane, because the plane was 1, 0, 1. And this is the type of example that explains why it's difficult to use this proposition. Because the fact that you have two charts for which the first fundamental form look different means nothing. The question is, can I change one of the charts in such a way that they become equal? I mean, okay, even on the same surface, I can take two charts of around the same point for which the first fundamental form look different. There's nothing. So, and in fact, this is exactly what's going to happen here. But I don't want to change this chart. I want to change, strange enough, I don't like the plane parameterized in this way. I want to change the parameterization of the plane, and actually I'm not going to take the whole plane, but I'm taking, maybe here the picture again could be a bit of help. Sorry?
Without origin, we need to take without the origin of plane.
For sure, I have, well, the origin I don't know. There will be some point which is a bit special because it will go near the vertex, no? I mean, so, but it's not enough to remove, I mean, I'm not going to take a point, the plane minus a point. That's, I have to do something a bit more, so I take x1 now, think of S1 to be the plane, to be x1 of uv, of the same uv, to be u cos v, u sine v, 0. Okay? So what's going on here? I mean, of course this lies inside the plane z equal to 0, right, in the horizontal plane. So this is a piece of the plane. Which piece? And why? And what am I doing? Well, so u goes from 0 plus infinity, so it's always half a line. Whatever point I put, so what I'm taking the circle, the v circle, no? And then for every point I'm adding the line passing through this point, half a line passing through this point. But am I taking the whole thing? The domain is the same, but the output on the plane, is it really the same? Now this is a little bit of a trick, but because I know it's a bit cheating. I mean, you say, well, the domain is the same, so the thing is the same. No, because you see, the angle of rotation is different. So if I restrict v to be in a smaller interval, whatever that is, now here I renormalize the angle in such a way that this becomes again 0 to pi. So in the cone, I'm doing the whole loop. But in the plane, I'm not going to do the whole loop. I'm starting from 0, angle 0, and I'm stopping at angle pi square root of 2. Okay? Whatever. Decide where is square root of 2. Okay? So I'm taking this part of the thing, and then I'm adding all half lines passing through these points. So what is this really actually? I mean, of course I can close it for a moment, even though then I will take the open part of this. So, and I'm taking this whole region here. Okay, I'm taking a piece of paper, I'm cutting an angle, and then I'm taking everything else. Okay, so this part, so this plays the game of the strip before, no? For the cylinder, everything was easy. I was really taking the identity. Now I'm reparametrizing a piece of the plane in this way. And now the question is, which are the coefficients of the first fundamental form of the plane, but with this chart? So don't tell me 1, 0, 1. This is a new chart. So the fact that it's always the plane doesn't matter. So which is E1, F1, G1, well now of course everything, unless I made a mistake, derivative with respect to u, and then I get 1. Now derivative with respect to u against the derivative with respect to v, I get 0 because of course the usual, this is minus sine cos plus cos, and they add to 0. When I take the derivative with respect to v, here I get u minus sine u cos. So this becomes u squared. Okay? Now, so, game over. Proposition. Again, you have the topological problem. half of the cone and the plane are not isometric because of topology, but they are locally isometric. Okay? We produce two charts. On the other hand, this kind of things is a little bit of magic. Okay? Because whether this, you see here, I guessed. In fact, of course, there is an obvious geometric intuition behind this. Because what are you doing? You are taking a piece of this plane and you are actually putting up and closing it. Okay? So, okay, this is a sufficiently simple transformation to visualize, and you can guess that maybe this is special and you try it. But in general, if I give you three functions on one side, and then I ask you, and then I give you another surface, and I say, can you find me a parameterization of this new surface in such a way these three functions are the first fundamental form, it's almost hopeless. Very rarely you can do it. Okay, of course, it's a system of PDEs, of partial differential equations. So whether you are lucky, whether geometry helps, I mean, certainly there is no theorem that tells you in general that you can do it or you cannot do it or so on. Okay? And in fact, well, there is a theorem. You can do it if, well, for sure there is an obstruction, and you can phrase geometrically the obstruction by the, but that's the next theorem we will study, by the fact that the Gauss curvature of the two surfaces have to be the same. Okay, so even though it's necessary but not sufficient. Okay, so. Very good. So I think we can stop here for today. We have analyzed the role of the first fundamental form in terms of length of curves and the possibility of being locally isometric or not, or globally isometric if you are particularly lucky that you can even solve the global problem behind everything. So the next step actually is to see which is the role of the first fundamental form, but for the next thing, which is the area of domains. I mean, the next thing you do in calculus after you compute the length of things is, of course, to compute the areas or the volumes of domains over in Rn. Okay. Now, next step is exactly, now, if I give you a surface and I take a domain over a surface, I want to be able to compute the area of this domain over this surface. And again, the first fundamental form is the one governing this, and we will analyze this. Of course, just one final comment. Typically, we have learned many instances where we spoke about isometric spaces and so on. And typically we said two things are isometric. If I take 2 points on one side, I measure the distance, and I go on the other side, there has to be a transformation which takes these 2 points with some distance to 2 points with the same distance. Here, what is this? I mean, why am I using this? I mean, so the word isometry and isometric should be kind of restricted, it has already a meaning in our mind. But you see, once we decide that isometry preserves length, this is actually more than, or at least in principle, it looks even more. Because then how do I turn a surface or anything where I can measure the length of curves into a metric space? Well, I define the distance between 2 points as the infimum of the lengths of the curves connecting these 2 points. So if I have a transformation which preserves length of curves, of course it preserves the infimum. So it will preserve so if I want to see any object like this as a metric space, I say, well, if you are able to compute the length of a curve, then you define the metric as the infimum of the length of curves. And now an isometry in this language is something which preserves the length of curves, so it preserves the distances. Okay? So it's okay. We are using a word isometry with a slightly stronger definition than usually we do for metric spaces. Okay? Because of course in principle you could preserve the infimum of the length of curves without preserving each competitor. Okay? So this is slightly more, but it's the right one in this situation. Okay?